see okay? Did Dasha come back yet? Did she find her phone? We skip. We'll come back to normal after the hypothesis testing. For my book, binomial hypothesis testing is on 136. Did you find it? Yeah. Did you get sorted, Sylvia? It's all finished. Yeah. Now, like I said, the reason I skip in normal distribution is because this lesson here continues nicely actually from what we did last week of binomial calculations with using the tables. So I think I'll swap these around in the next workbook and do this one next. Okay, so to get started, I'll just give you a little question to think about, just to get us thinking about what we need to cover here. Now, I think maybe Column has talked to you about this topic already in a not precisely this, but kind of the concept behind it, the idea of a hypothesis. No, like, is this a word you know from biology? A hypothesis? Yeah. So how did Colin explain it to you? So how do you know it then? Did he use it in class? And how did he use it? Yeah. What's another word for it?
Theory.
Like theory, yeah. What else? Guys, come on. Yeah, like a prediction, yeah, or another word like a claim, maybe. Yeah. So, anyways, I'm going to give you a little example, and I want you to think about what the problem is here, or how we could check it. Okay. Second. Okay, so for example, so imagine somebody can claim, I think the example here is, no. Claim they can taste if the milk was added first or last to the tea. Okay, so this person can tell if they put the milk in first or if you put the milk in last. Okay, now this is the claim that they're making, so I want us to think about how we could test this claim that the person is making. So I'll give you a minute to think about what you could do, maybe as an experiment or something, to test this claim that the person can tell from taste alone if the milk was added first and then the tea, or the tea and then the milk. So just think for a minute, and then we'll see how we could test this. Now you might need to give me some numbers as well if you have an experiment, like how many times to, or whatever. Okay. Dasha, did you find it?
Yeah.
What room were you in this morning? You picked it up? Yeah. Okay, so panic over now. You can let your heart rate lower back down and just relax now. Yeah. Okay, anyways. Any ideas how we can test this? So what do you suggest that we do to test this?
I think you should have a control and you see the doubts in it.
Yeah, okay, so you should have T.
With doubts in it.
No, not this. Yeah, what do you think?
You can get 20 cups of
20 cups, okay, good.
Say 10 have
The milk,
milk,
yep, and 10,
10 have milk.
yep, good.
You can let this person taste at intervals of maybe 5 minutes.
Yeah, okay. And then, how would we know if their claim was right or not?
I mean, we know it.
Well, I mean, what type of result would you need to see so you know that their claim is true?
How did he do it?
No.
So, yeah,
Well, okay.
you graph it against.
Oh no, guys, come on. You're making hard work of this when it's not. You nearly had it. I just want to know what type of results would we need to see to believe the person.
Half of it true.
No.
50%.
No, definitely not 50%.
What?
Yeah, but this is okay. So this is the point, right? Suppose the person's claim is false, and we did this experiment where we had them test and taste 20 cups of tea, and as you said, half of them the milk was first, and half of them the milk was last. Okay, if the person couldn't tell the difference and they were just guessing, how many would we expect them to get right from just guessing?
Half of it.
Yeah, half of it, 10 of them. Right? If they were just guessing, yeah? But suppose that they got 11 of them right from guessing. Do we think they can tell a little bit, or they're still guessing? Yeah, but what if they got 19 of them right?
Wrong.
Do we still think they're guessing?
Wrong. They don't know what
No.
you're doing.
If they got 20 right, we think that is genuine.
No.
Well, maybe if somebody got 20 right.
Yeah.
Okay. What about if we gave them 100 cups and they got 100 right? Okay, that's quite certain, right? What about 62? No, we're not so sure, okay? So the idea behind this lesson is we want to quantify, we want to calculate at what point do we say, okay, enough results have come back positive, so we think that the claim is true. You understand? We're trying to set an actual number. We'll say at this point we believe the person, but before this we don't believe it. You get the idea? So we need a little bit of vocabulary here to help us out. Okay, so the first one is null hypothesis. Now maybe this is even a word you would know from biology class or chemistry or any other science subject. Null hypothesis. No, it doesn't actually, even though it's null. Yeah, it's not. It sounds like it should be nothing. Not quite this. Does anyone know null hypothesis? No. No, yeah, I understand you're all thinking null or nothing or false because of this here. So the null hypothesis is the hypothesis to be tested. Now, the purpose of the null in it as an adjective means that there's nothing special here. So this hypothesis has to be, not special. So let's go back to the example of our tea drinker who says they can tell if the milk was added first or second. Is the null hypothesis that they can tell a difference or that they can't tell a difference? They can or cannot. What would be the null hypothesis? And remember, it's the hypothesis to be tested, and you say there's nothing special in the hypothesis. Can or cannot? Cannot. Okay? Because that's what you might say the non-special version. Like the normal, the basic, the typical. Yeah. So we don't say that we're testing if they can tell a difference. We're testing that they can't tell a difference. This is the null situation, the normal situation. Do you understand the null part of it? Yeah. So the second word is called the alternative hypothesis. Yeah. Oh, yeah. There's some symbols here too, isn't there? Yeah. Just for symbols. Yeah. You can call this H0 and then H1 or HA. Yeah. Does anyone? Well, you could probably guess here. The alternative hypothesis is the opposite, nearly.
The right.
Yeah. Yeah, it's kind of like the counter null, the opposite, the special. So in the example of our tea drinker,
You can taste.
that they can taste the difference.
It's HA, right?
Yes. Yeah. Okay. Are we okay with those two pieces of vocabulary? Now that's important to know. It seems simple, but you don't want to mix this up, especially when you're doing any kind of research, okay? Because you'll look like an idiot, all right? So when you're typing up your paper or whatever it is that you're researching, okay, don't mix the two of them up. Right, next bit of vocabulary. We have a test, but there's actually two types of tests. There's a one-tail test or a two-tail test.
So these are words or?
Yes.
There are two types of tests. There's one called a one-tail test and there's one called a two-tail test. And we need to understand what's the difference between them before we begin calculating. Which we need to know which situation we're in. Is it one-tail or two-tail? Now the difference between them can sometimes be very, very hard to tell. Okay, it's not as easy as with the null and the alternative. Ray, come on. Look, this is not easy stuff, okay? You need to listen carefully. So as I was saying, null and alternative, it's kind of easy to tell the difference there, okay? Because it's easy to identify which is the special situation and which is the non-special situation. One-tail and two-tail is not as easy to tell the difference. And I'll give you an example of the difference. Can I scroll down? Yep. Okay. So, I'm going to give you two situations that demonstrate the difference. So I'll say situation A is maybe you're testing some new cold medicine or some new flu drug of some kind. Okay, so we have some kind of flu drug, and the hypothesis that you're testing, well, you might get this, that it has no effect. This is A or F? A or E? A.
E, I guess.
But it's been used as a verb. Oh, okay, whatever. No effect. Okay, fine, whatever. An alternative, maybe it reduces your recovery time, your illness time by, let's say, 3 days. So reduces by, let's say, 3 days. Okay, that's situation A. Situation B, we'll keep it the same. We got a flu drug, and the null hypothesis and the alternative. So the null hypothesis is it has no effect again, because that's the non-special situation, and the alternative, it has an effect. Now you might say, well, there doesn't seem to be a huge difference between the two, but there is a situation, there is a possibility that is included in B, but is not included in A. There is a distinction between A and B here. Can we see what the distinction is? What is the difference between A and B? Yeah, you think you know? Go on. No? Okay. Say again? Yeah, how is the alternative different?
So B has an effect.
Yeah.
For A, it just reduces the
Yeah, so what's not being considered in A?
A doesn't consider the effect of the drug on the alternative hypothesis.
No, not quite that. Yeah?
Maybe A reduces it by 3 days,
Yeah.
but B, let's say the fast
Oh, good, okay, yep. So I'll say reduces by 3 days or more. There now, okay. Yep. Yep, you're right, that's true. But look, the other thing is this. It's possible that the drug increases your recovery time. It makes you sicker. Right? I mean, these things could happen when you're designing new treatments, right? So, in situation A, this is only testing the possibility that the drug has no effect or it makes you better, quicker. Whereas in situation B, you're testing that the drug has no effect versus it has an effect. And here, has an effect could be makes you sicker or it makes you better. Whereas here, has an effect just means it makes you better. So did you hear the difference? Here, has an effect means it could make you sicker or better. 2 tails. Here, it has no effect or it makes you better. 1 tail. This is the difference between 1 and 2 tails. Okay, so this is an example of 1 tail, and this is an example of 2 tails. Okay, so you should write this example down. And as soon as we know the null hypothesis and the alternative hypothesis, and if it's 1 tail or 2 tail, then we can begin calculating and testing the hypothesis if the claim we think is true or false. Okay, do you have that written down? No. Now, I probably have already talked much more about this than you would have heard in biology, perhaps? Yeah? Okay. Can I scroll down? Yeah. Well, while we're waiting, the little question I want you to have to think about is, imagine our tea taster tested 5 drinks, and they got all 5 drinks correct, but they can't really tell a difference, and they only got it right because they guessed. What's the chances that they would get the 5 drinks correct from only guessing? All 5 right from only guessing. So it's it's a binomial problem, isn't it? How many trials are there? And how many successes? And the probability of a single success by guessing? 1 over 2. Yeah. So what is the probability, please, of guessing all 5 correctly from only guessing? You might need a calculator for this. No, that doesn't quite sound right. I was thinking it more nearer to the 3% mark. About 3%, isn't it? So I want you to consider this possibility, that you gave the person the 5 cups of tea, they drank the 5 cups, they correctly identified it, but they only got them right because they guessed. How often would that happen? 3% of the time. There's a 3% chance that they just got lucky. Okay? But from looking at the results, you might conclude that they could really tell the difference. So have you reached the correct interpretation or not? The correct conclusion? No. They only got it right because they guessed. But they guessed the 5 correct. So now you think that they can tell a difference. Okay? So we actually gave vocabulary for this before, where you get the wrong result. Do you remember? And you might have mentioned this in biology. Do you remember what that's called? That's like a false positive. Yeah. And you have the opposite, false negative. Okay, so this is something to consider. Anyways, let's do some calculations and we'll talk more about this vocabulary. So we have something called a p-value, and please don't confuse that with p. These are two different things. So p-value, as like one word, that is the probability of the data or more extreme, assuming H0 is true. So that number you calculated for me a moment ago, that's an example of a p-value. We're saying there's a 3% chance that they got that right, assuming the null hypothesis, which is that they're guessing. Now, I'll flesh this out with an actual example now, okay? So, can I scroll down? Can I scroll down? Yeah? Okay, let's have a look at an example now. So I'll keep the numbers small at the moment. Let's say we have a test where, okay, let's keep it an example. Let's just say we keep it simple. We want to test if something is an acid. No, that's too complicated. Oh, we'll just go back to our tea drinker. Okay, so we have our tea drinker, and let's say we properly want to test if they can really tell the difference here. So our null hypothesis, what is the difference here? Or what is the null hypothesis here for our tea drinker? That they can or cannot? Yeah. They can't tell a difference. Now, carefully, what is our alternative here? Yeah, that they can tell a difference. Now, again, carefully. Think carefully. Is this one or two-tailed test?
One, two, two. Or to your right, or no, one. I guess.
It's two. Okay? Because the reason it's two tails is we're testing that they can tell a difference. And for them to, what's potentially them telling the difference between the milk being first or last? Well, that's if they get everything right. So when you put the milk in first, they say that the milk is in first, right? Or the other side, that they get everything wrong. Believe it or not, that's telling the difference if they get everything wrong. Imagine somebody can tell if the milk was put in first or last, but they always get it wrong. So you put the milk in first, and they say it went in last. You put the milk in last, they say it went in first. They get it wrong, but they get it wrong every time. Can they tell a difference? Yeah, but they've just labelled it the wrong way around. But they can still tell a difference. Do you understand? Yeah. So it seems strange to say this, but if they get everything exactly wrong, then they can tell a difference. Yeah. And it means if they tell you the milk went in last, then you know the milk went in first. If they can really tell a difference. Okay, so this is actually two-tailed. Okay, and let me give you some numbers. Let's say that we gave them 20 cups of tea. And let's say the number that they got right, let's say they got 15 right. Okay, so before I do the calculation, I'll let you write this down. By the way, in the exam, you do get marks for writing this down before you do any calculations. So in the exam, you would get, I think, actually 1 mark and 1 mark. So you already have 2 marks. Yeah?
How did you know it's like 20 cups?
Oh, sorry. And this here is given. That you did an experiment with 20 cups of tea and they got 15 of them right. Okay. Whoa. Okay, did you write that down?
No.
No?
Would it be like 20?
No, 2-2.
Yeah, but when?
Well, this is what I'm saying. It's very difficult to tell the difference. It's 2-tail when you have a look at both possibilities. Like they're always right or they're always wrong. And it's 1-tail if you're only looking at the possibility that they're always right. So a 1-tail situation would be they can't tell a difference versus they can correctly predict. Yeah? Yes?
Yeah, what if one of the 2 tails linked to normal distribution? Just they give you a standard deviation.
Oh yeah, well we skipped normal distribution.
Oh.
We don't worry about hypothesis testing with normal distribution for this program, yeah?
I have a question. So is it like the 2 tails, like we said, is it 2 tails according to the H0 and H1, H3?
No. Well, yeah, actually, no, yeah, it is.
Like for example, if HA, he can't taste a slight, not slight difference, like...
No, I know what you're saying. For 1-tail, you would say H0 the same, but HA is they can predict correctly if milk was added first or last. Then it's a 1-tail. Okay, so now let's have a look at the calculation. So, we calculate what's called the p-value. The p-value here is the probability of getting the data. So in this case, that would be 15 right.
Over 20?
Or more extreme. So that would be getting 15 right or 16 right or 17, 18, 19, 20. But we have to be careful. There's another possibility. They could get 15 right, but the other tail is 15 wrong. Yeah, which would mean 5 right, 4 right, 3 right, 2 right, 1 right, or 0.
Oh, you said 15.
Sorry. 15 right, 16 right, 17, 18, 19, or 20 right. Or 15 wrong, which would be 5 right, 4 right, 3 right, 2, 1, and 0.
There's at least 15 right. Like there's at least 15 right.
Hmm?
That's what we did for the first
Yep.
one. And we did the at least 15 wrong.
Yeah, 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 yeah. So we're looking at the 2 tails, because remember I said a moment ago, we would believe this person's claim if they got most of them right or most of them wrong. That's the test here. If somebody says they can tell a difference between it, we would believe them if they got most of them or all of them right, or most of them or all of them wrong. That's the meaning of the 2 tails here.
So
Yeah.
you said...
One at a time, yeah?
What about 10, 11, 12, 13?
Yeah, because remember the formula I gave you earlier for p-value? What did I say it was? Did you write it down? Oh, I see it.
Ah, yeah.
Yeah. What's the p-value? The probability of the data or more extreme. Not less extreme, more extreme. Yeah? No? Maybe.
Why?
Wait. If somebody gets 17 right, what is a more extreme result in their favour? That they get 18 right, or 19, or even all of them. That's more extreme, isn't it? Yeah. Less extreme would be if they got 10 of them right. Yeah? Question? Question?
you said like 15 is right,
Yeah.
more extreme.
Yeah.
And you said like 15 is wrong.
Yeah.
Why did you write 5 for
15 wrong is 5 right, isn't it? Yeah.
But they're 20.
my brain?
You're like, okay.
Yeah. Questions? Guys, I haven't actually done a calculation yet.
Yeah, either. So, why should I add 0?
The most extreme wrong result is they get 0 right. Now, hey guys, I need you focused now, unless you're a genius at this.
We are.
Special, I suppose. No, sit down. Sit down. What are you getting? Now, I need your full attention because this stuff isn't easy. Is there any other questions on this now? We'll do more examples, okay? So, p-value 15 or more or 5 or less. They're both ends of the tails, okay? Now, we will break this up into 2 problems, okay? So, I'll do the first one on the left here because we can use our table book here. We want 15 or more successes. You know where this is going, okay? Now, what's the p here? 0.5. The n, 20, and the x, 15. However, there's a small problem. Remember the tables we were using last week? Does that answer or more, or does it answer or fewer, doesn't it? So 15 or more successes, we need to change that into failures. So I'll just write a little tick here for success. So 15 successes is how many failures? 5 failures or fewer. Now, what's the p-value for a failure?
0.5.
And n? 20. And x is now 5. So, what value do you get here in the table book? Yeah? Can you look up the tables? I know, this topic is very difficult every year because it's very conceptual. Lots of concepts. Do we have a number here? 0.0207. Okay, now let's look at the other possibilities. This one is the probability of 5 or fewer successes, right? That's p equals 0.5, n equals 20, and x equals 5. Now, looks familiar, doesn't it? It's the same, isn't it?
But isn't it we have to like, no, it's not.
Right, if you add these two together, what do we get?
4,
Hang on.
4.
0.0414. Now, what's wrong?
Aren't we supposed to 1 minus 0.207 on the
Yeah,
first
right.
one?
On the first one?
Yeah.
Yeah, because we
No.
converted, like we changed. We have to be
We didn't use the not.
Oh.
We just changed the statement about successes into a statement about failures. We didn't use the not. We didn't say not 15 or more.
So we can actually
Right.
do this instead of using the box.
Is that a, yeah, you could have used the not as well. Not 15 or more. It might have simplified. This just seemed the easiest thing for me to do. Isn't, guys, we agree that these two statements are the same, aren't they? If I said 15 or more successes, that's the same, exact same as saying 5 or fewer failures. There's no difference between the two. It's equivalent. Yeah. Now, here is where you make the decision. Yes? You put your hand up so you have a question. Has it not loaded in your brain? What's the question? Are we having some buffering issues here? What's the question? Come on.
Never mind.
Never mind. 404. Okay. Right. Now, this is where we make the decision. We convert this normally into a percentage, 4.14%. If the p-value is less than 5%, then what we do is we reject the null hypothesis.
Well, why the null hypothesis? Is it not?
Yeah, I'll talk about that in a moment. And if the p-value is more than 5%, then, which we actually write as we do not reject the null hypothesis. Now, your question is the 5% a constant? Yes. 5% is the standard value used in research. It's not a rule, it's a standard.
But if you have like 5% exactly,
Yeah.
research is it rejected or not rejected?
Flip a coin. It's not clear if it's exactly 5%, and I doubt that you can technically get exactly 5%. I think you have to make a decision at the start of your research about what you would do in that situation, but that hardly ever happens. Because I don't think any value is going to be 0.0500 exact, you know? Anyways, not to worry, because often what happens is a computer does the calculation more accurately than the table book, so I mean it's not likely to be 5%, yeah?
It's always the H0?
Yeah. Provided that you correctly identified the H0, you reject the H0 in the test. So, in this test here, we got a p-value of 4%. So, do we reject or do we not reject the null hypothesis?
Reject.
The conclusion is we are to reject the null hypothesis. Now, think about what that's saying. If we reject the null hypothesis, are we saying basically that the person can or cannot tell a difference? Can tell a difference. Because, we've rejected the hypothesis that they cannot. Remember what we said at the beginning? Null hypothesis is they can't tell a difference, which we've just rejected.
So like we got a lower percentage on
One.
cannot, we got a lower percentage and he cannot tell the difference, right? So there is more percentage in his like...
No, it's difficult to interpret these numbers here. They're just rules. If you get less than 5%, you reject. If you get more than 5%, you do not reject. It's a standard, it's a test, it's a rule.
Why you cannot like take the H8
What?
instead of H0?
Here,
Yeah.
the p-value calculation is using the null hypothesis.
Oh.
The null hypothesis is that they can't tell the difference, and so they're only guessing. So that's the 0.5 there. So it should be the H0 here. Okay. Yeah, look, I know this is difficult. I was kind of planning on using the two classes for this lesson, because what I'd like to do is to alternate the questions. We try them together. Okay? Because we really need to practice these. This is really important because you're all going to be using these calculations in any kind of research, because you need to have a way to test claims that are being made. Okay? So, we'll do these together. Do you have this written down? Yeah.
So the answer is he can't
Reject H0. So basically, what does that mean? That we think that they can tell a difference. Now, are we certain that they can tell a difference? No, because it's still possible that they got it right from guessing.
But if it was 0%, it's like 100%. Like
If the p-value was 0, actually, I don't think it could ever be exactly 0. Because when you look at the table book values, I think the most extreme value is 0.9999 or 0.0001. So you can never get exactly 0 here, but it can be so close to 0 that you can be very confident with your result. Yeah. Basically, as Hazard was saying here, the p-value, really the smaller that number is, it gives us more confidence in our rejection of H0. And 5% is the threshold. Once we go below 5%, we reject the null hypothesis. But when that p-value gets smaller and smaller, then it just gives us more confidence that we were right to reject the H0. Yep.
So it's false, so we're not so confident that we can
Say again? If
since like the threshold is 5.
yeah, we haven't exactly jumped far away from 5, have we? So technically speaking, from a research point of view, we are right to reject the null hypothesis, but as you suggest, we might be wrong. And so we will be justified in doing the experiment again, if we wanted to. Yeah. But if we got a p-value of 0.0001, it's quite strong. Okay, can we look at these together now? Yeah. Can I scroll down? Yeah. Well, we'll do question 1 and 2 together, but then I'll give you a minute to try the calculation in number 3. Number 1. A die is rolled many times in a board game. The player is considering whether the die shows more 6s than it should. That is, she feels the number 6 came up too many times and now is questioning whether the die is fair. So, is this a 1 or 2 tail test? It's 1. And let's check that it's 1, because what's the null hypothesis? What's the null hypothesis? The die is fair. Because remember, the null hypothesis is the non-special hypothesis. Right? So, what is the alternative hypothesis? No, that doesn't quite answer what she's testing. The alternative hypothesis is that the die is favoured towards the 6. It's loaded towards the 6. Yeah. So, is this 1 or 2 tail? It is 1 tail. Null hypothesis, the die is fair. Alternative, the die is loaded or biased towards the 6 outcome. Yes? Do you want to write that down and we'll continue?
Can you repeat the question?
Huh?
Can you explain why it's 2 tail?
Well, it's not 2 tail, it's 1 tail.
No, why it's 1 or 2 tail?
It depends on what you say the alternative is. So what's the alternative hypothesis here? That the die is favoured towards the 6. That's only one direction, one possibility. David, you suggested for the alternative that the die is loaded, unfair. That would be 2 tail, because it could be unfair in both directions. It could have the 6 too much or not enough. So that would be 2 tail. We're getting the idea? Yeah? No? Might have to sleep on it. We'll do more examples, okay?
The next one.
Yeah. Did you write the answer down? Yep.
Question.
Yeah.
Our 1 or 2 tails depends on our alternative hypothesis, because if we say like it's unfair, like
Yeah, that's 2 tail then.
But we can, for example, have one side of face and the other side of 6, 6, 6, 6, 6, 6, 6.
Yeah.
It's only unfair.
Yeah.
But we said alternative hypothesis is what?
That it's favoured towards 6.
Like all sides is 6.
Not that 6 shows up more than it should. So, like, you might get something like 2, 3, 6, 6, 6, 2, 1, 5, 6, 6, 6. You know, that 6 is coming up too often. You said that it's unfair. That's 2 tails, because you could have a situation where you get 6 too many times, or you hardly ever get 6.
Yeah.
That would make it 2 tails.
Yeah, but here
Yeah.
So it cannot be less 60.
Yeah, so it's one tail. Yeah. We'll do another example. The next one. A boy tosses a coin 100 times and would like to know if the coin is fair or if it's biased. So is this one or two tails? Two tails. Because there are two ways to be biased. You could have head show up too many times or head show up not enough. So this is a two-tail test. What is the null hypothesis? What's the null hypothesis? That the coin is fair. And the alternative hypothesis? That the coin is biased or unfair. Okay, I think our brains are starting... Yeah, there we go. Our brains are starting to wrap around this. Excellent.
I just got the null hypothesis and the alternative, but I didn't get the...
Okay, one step at a time, huh? All right. Good, good. We're making steady progress. Yeah? That's fair.
That's fair. And the alternative is like, it's biased.
Yeah, yeah.
But do we need to demonstrate bias like can be head or tail?
No, that's okay. You can just say it's biased. It's understood here. Right, here's a little bit, a couple of more examples before we do calculations. So, number 3. 3 students are playing a game with a die in a casino, and they each suspect that a 1 shows up more than it should. What are the hypotheses for this claim? So, the first student thinks the 1 is showing up more than it should. So, what's the null hypothesis? It's fair. And the alternative? Favor towards 1, loaded towards 1.
How is it fair?
No, the null hypothesis is always that it's fair. It's not special. Yeah? Yes? Okay.
Does it sometimes like the null hypothesis be special?
Nah, should never be. Should never be. Okay. Did you write that down? Null hypothesis is that the die is fair, and the alternative hypothesis is that the die is loaded or biased towards the 1 outcome. Yeah? Question, yeah?
The previous question.
Yeah.
In the answer, I think it's wrong.
Did I say 1 tail? That should have said 2 tail. Thank you for pointing that out.
You have to fix it. For the next generation.
Where?
No, my answer is wrong for number 2 in the book. It should have said 2 tailed. Okay. B, 3B. A 1 does not show up as often as it should. Right, what about this one? The student wants to know this. A 1 does not show up as often as it should. Null hypothesis? Null hypothesis? It's fair.
Null always fair.
Thank you, Hazza. Yes? Yeah.
And one does not show
Again.
Ah, guys, come on. The null hypothesis is that the die is fair, as it always is, right? And the alternative hypothesis,
bias in different numbers because
yeah, that's just biased, isn't it? A 1 does. Oh no. A 1, yeah, it's biased, as you said, to the other numbers. Yeah, so you could say it's biased against 1.
or different
Away from 1. Yeah. Or if you want bias towards the other numbers. Yeah. Okay. And then lastly, a 1 shows up less than it should. What's the null hypothesis? Fair. And the alternative?
the same.
Wait, it shows less than it should.
Yeah.
It's not fair. No, it's a null hypothesis. It's
Null hypothesis is that it's fair. And the alternative?
Show less than should.
Yeah. So what does that mean? It's bias against 1.
So the same.
It's the same, isn't it? Yeah.
But shouldn't we like calculate something, or do we just?
No, for these questions, we're just practicing null hypothesis and alternative hypothesis. So I have one more question where we practice. And then we'll do a calculation. Okay. 007 is given a sample of drinks which have either been shaken or stirred. The sample contains half of each. We, as the researcher, would like to know if Mr. Bond can tell the difference between shaken or stirred. Is this a one or two-tailed test?
No, one.
Two.
Because it's regular, like it's normal. They shake the drink. But
This should remind us of our tea drinker. It's two-tailed. Because we believe Mr. Bond can tell the difference if he gets them all right or all wrong. So it's two-tailed. We have evidence to believe he can tell a difference if he correctly predicts all of them or incorrectly predicts all of them. So it's a two-tailed. Yeah? Okay. Now the next one. If instead we as the researcher would like to know if Mr. Bond can predict if a drink was either shaken or stirred, then is this a one or two-tailed test? One tail now.
Is it just one drink?
Two. No, one.
It's one drink.
If instead we
Yeah, one. Yeah. Because we're only considering his correct predictions.
because it's one drink.
Yeah. Because think about it like this. If he predicted everything was wrong,
So you cannot predict.
then he can't predict if it's right, because he just predicted wrong. Now, it's still interesting that he got everything wrong, but we can confidently say he can't predict the right drink. It's one tail. Yeah? I know, look guys, I know this is mentally quite difficult. I know. But this is why we're taking our time doing this, okay? And you need to tell the difference. Okay? Yep.
Can you just repeat one more time?
Okay, so I'll repeat one more time. I'll do A and B. In situation A, this is two-tail, because more extreme means that he either gets everything right or he gets everything wrong. If he says, I can tell a difference, and he predicts every drink wrong, exactly opposite, then he can't tell a difference. It's just he can't correctly label the difference. The drink was shaken, he said stirred. The drink was stirred, he said shaken, but he was right. Just the wrong way around. So you can't tell the difference. Okay? In situation 2, we only want to know or care about if he can correctly predict the drink. So if he predicts everything right, great. We believe him. If he predicts everything wrong, we don't believe him. So it's only one tail now. Because we only consider half the situation as the previous case. Yeah? Are you okay? Can you hold this in your brain, and we'll now do an actual calculation one, okay? So what I'll do is I'll do number 5, and then let you try number 6. So let's look at number 5 together. A coin is tossed 10 times, and heads is observed 3 times. Carry out a hypothesis test on whether or not the coin is fair at the 5% level. The 5% level meaning 5% is the threshold in our calculation. Right, so the first thing is we have to state the null and the alternative. Well, we know the null. Coin is fair. Now, we have to be really careful here. Are we testing that the coin is unfair or that it's biased towards heads? Let's read the question again. Carry out a hypothesis test on whether or not the coin is fair. So what's the alternative here? Coin is unfair. Therefore, one or two tail.
Why isn't it heads? Because it said 10 times and heads.
Yeah, but it's because of the instruction. I said, carry out a hypothesis test on whether or not the coin is fair. Not, what would I have to say if I wanted one tail? I would have said, carry out a hypothesis test on whether or not the coin is favoured towards heads.
Or biased.
Yeah, or biased towards heads or whatever. Yeah. Okay? Let's do our calculation now. P-value. So, how many times did heads show up here? 3. So just to keep it simple, okay, we'll call heads success and tails failure. So p-value will be the probability of getting 3 heads or more extreme. What would be a more extreme result? 2, 1, 0. But on the other side of the spectrum, at the other side of the tail, getting 3 heads is extreme, but the other extreme end would be getting 17 heads.
No. 7, 8.
Oh, sorry, there's 10 of them, thank you. 7, 8, 9, or 10. If you prefer, you can think about it this way. What is a non-extreme outcome if the number of heads is equal to 5? Agreed? If you flip a coin 10 times and you get 5 heads, would that be extreme or not extreme? It would be not extreme. In fact, that's what you expect. So extreme here means to be away from the center at both tails. Getting either too many heads or too few. Now, it's a little bit easier here if we split this up into 2 calculations. That is 3 or fewer plus 7 or more. Now this one is nice, isn't it? Because we have the tables already for this. N equals 10, X equals 3, and P equals 0.5 for fair.
How did you know it's 0.5?
Yeah, because that's a good question. How do we know the P is 0.5? This P is always the value you would get in this assumption. If you assume the null hypothesis that the coin is fair, what should the P be? It should be 0.5. Yeah, if 50-50.
What about the alternative?
We don't know what the p-value is in the alternative because we don't know how unfair the coin is.
So like the n, if the n was 8?
The p is still 0.5.
How?
And what about...
Wait, one at a time. I flip a coin.
Okay.
The coin is fair.
Yeah, okay.
How likely is it I'll get heads?
Same,
That's it. That's why it's 0.5.
just like a 50-50.
If it's fair. Yeah?
Bias
Bias it depends. And so we can never do this calculation. We can never do this calculation. Alright. I need to change this statement of 7 or more into a fewer statement. So 7 or more successes would be 3 or fewer failures. So let me just put a little tick here to mean success and a little X here to mean... Oh, by the way, in the exam, don't do that. Actually write the sentence out. 3 or fewer failures, okay? Now, in the 3 or fewer case, what's the N? 10, X, 3 and P. Now, we've done 2 of these examples, and have you noticed in both cases, for these types of problems, both tails are the same, yeah. So that's actually quite common, that it's symmetric.
Can we just multiply?
Yes, you can. So the answer will just be twice whatever you got in the tables.
3, 4, 3, 8.
Are you giving me the final answer, or
Times 0.1719.
17? Okay, I don't even need to calculate it. Clearly that's much more than...
Less.
No, it's more.
0.4.
Yeah, more, yeah.
Yeah?
What? Why?
Because it's 17.
Oh, okay, okay.
Isn't it?
It's 34.
That's 34%.
Yeah, that's more than 5%.
Thank you, Professor David, on that observation.
I'll check. I went into all the times through.
This is bad.
Guys, we don't even need to check. We clearly know it's more than 5%.
But it's
Yeah.
not 0.1.
Yeah, okay.
Okay, so reject or do not reject?
Do not.
So our coin is unfair.
It's fair.
It's fair, yeah. Now guys, you might have guessed that at the beginning. If you flip a coin 10 times and head shows up 3 times, how many times was it supposed to show up? 5. we kind of know that 3 isn't too far away from what we expected. It's not like it showed up once, you know? So we could have guessed that this is probably what we were going to end up with at the end anyways. That we do not reject. And so we have some evidence that the coin is fair. Now, imagine we flip the coin 1,000 times and 300 times it came up as heads. Well, that would be a different situation.
But the ratio.
I know, but the number of trials was much different. We could have got those 2 tails. Remember, tails came up twice more than we expected here. We got 3 heads. How many were we expecting? 5. So how many times did we get tails when we shouldn't have? 2. Could have been by luck. Flip the coin 1,000 times. Is it likely that 200 times I got tails by luck? No. So it's not just the ratio, it's also the absolute number. Yeah? Okay, now I'm going to let you try number 6 before I do it. This is your first example by yourself. Is it 1 or 2?
1.
Good. Okay. Mhm. Okay, you should be finishing this up now. So, anyone got answers?
It's 0.
So reject or do not reject? Do not reject. Are you sure, man? So imagine, Carol, imagine I roll a die 20 times and half the time I got a 6.
Reject.
I think I should reject the claim that it's a fair die. right?
Oh, okay, yeah.
Right, let's have a look. So please look carefully. First things first, what is the null hypothesis?
Unfair, right?
Null hypothesis.
Why it's always fair?
And now, look, Haza, I have on recording here that you understood this 10 minutes ago. Okay? I have video evidence here that you understood this, alright?
No, because it's biased.
No. Look. Go back to 10 minutes ago when you understood this. I think it fell out of your head. You did understand this. I saw it in your eyes 10 minutes ago. Right. A fair die. Null hypothesis. Why is this the null hypothesis? It's always the null hypothesis. It's always fair. Why? Because it's always the not special. Remember? Yeah, okay. Now, what's the alternative here?
Biased towards 6.
It's biased towards the 6, isn't it? Yeah. So I'll just write bias towards 6. Okay. Right. And so is this one or two tails? One tail test. Okay. Just a sip of coffee first. Okay, so look. The reason this one is 1 and not 2 is because we're only looking at the possibility that it's bias towards 6 showing up more than it should. Okay. What would it need to be two-tailed here?
Just bias.
Just that it's bias.
Yeah.
But bias towards 6 means that you're getting 6 more than you should. Two-tailed would be you're getting 6 more than you should, or the other extreme, less than you should. I suppose it's because I use this word. Maybe it's the grammar here. You understand when I say bias towards 6, I'm saying that 6 comes up more than it should. Yeah? How would I change the language so that I would just mean I'm not getting 6 as many times as I expect? Yeah, but in both directions.
Bias towards 6. No.
Bias toward other except
6.
Oh,
Towards 6 and other numbers.
just unfair at 6, you know? Yeah,
So it's
yeah.
or bias towards all numbers except 6.
But that's one tail. It's just it's the other side of the tail. You see?
Just bias got
this is complicated.
The simplest way to say this is two-tail is it's fair, or the alternative is it's unfair. Guys, hey, now look. Okay, let me just put it this way. It's probably easiest to know if it's two-tail or not. And if it's not two-tail, then it has to be one-tail. And how can we tell it's two-tail? Two-tail is when you have both extremes possible. So two-tail here would be it's fair, or the alternative is that it's unfair. How can it be unfair? In two directions. Either 6 is coming up too much, or too few. Okay. If it's not two-tail, then has to be one-tail. Yeah, because it's not two-tail. And two-tail would just mean bias, end of story, either way. Alright? Okay. One-tail. P-value. Now, we'll call getting a 6 a success and not getting a 6 a failure. So, how many successes are there in the data here? 10. And what would be more extreme? 10 or more?
We always take the more extreme.
Yeah. 10 or more 6s. I'll write a 6 in a box here. Okay? However, does our tables allow us to calculate or more? No, so we'll have to change this into a statement about or fewer. So 10 or more 6s would be, is there 20? Yeah. 10 or fewer not 6s. Failures. Yeah? Yeah? Okay. Now, let's see. Can we use the tables? N equals 20. X equals 10. And P equals, now just be careful. Be careful, it's 10 or fewer not 6s. Yeah, which is 5 over 6. You have a die, you roll a die. What's your chance of not getting a 6? 5 over 6. Yeah? Yeah? So what's the P here? 0.83. Yeah. However, I know from our table books we can't go up in this amount. It goes up in 0.05s or something, doesn't it? So I have to approximate this as what would be closest, 0.8 or 0.85? 85. Now, we've seen this problem before, haven't we? Does our table book go to 0.85? No. So now what do? We have to convert again. What way can we convert? 1 minus the probability of not 10 or fewer, and I'll just write X's for failures. Okay. Now, what does it mean to say not 10 or fewer? No, I mean change the statement, get rid of the not. Not 10 or fewer.
Isn't it back to the first sentence?
Come on. No. You see, you knew this last class. Not 10 or fewer.
10 or more.
No. No. 11 or more.
Oh, yeah.
Yeah. Yeah. Yeah.
Right now.
Yeah, so pay attention. Okay. Now we're back to our problem at the beginning. Aren't we?
Yeah.
Yeah. Oh.
Wait, what?
Yeah, something went wrong here. Yeah, we have to go back a step. Yeah, we have to go back a step, yeah. Yeah. Oh yeah, sorry, I apologize, yeah. I forgot what I'm trying to fix. The problem is not with the or fewer. What's the problem with? The probability. Yeah, so we need to change it to a statement about successes. Yeah, thank you, right? So, 10 or fewer failures. Can we make that a statement about successes?
11 or more.
What did I say?
11 or more. 6.
Oh yeah. Sorry.
Like what?
Yeah, no, I see now what the problem is. Let me scroll down. So here, 10 or more 6s, okay? I jumped the gun a little bit when I was looking at the tables here. I jumped the gun a bit. What's the probability of getting a 6? 1 over 6. Is that in the table book?
Yeah.
Well, roughly. 0.15. Yeah? X equal, or N equals 20 and X equals 10. I thought the problem was here. That was my mistake. It's not here. What's the problem with this statement? This is fine. What's the problem with this?
More.
The or more part, isn't it? That's what I should have fixed. I was trying to fix something that wasn't broken. Yeah, thank you. So I should have fixed the or more. Yeah. So how do I change this now into or fewer? Yeah, but I could use the not trick, couldn't I? Yeah. 1 minus the probability of not 10 or more 6s. And what's the meaning of not 10 or more? Not 10 or more. Very good. 9 or fewer 6s. Now can I use the table book? Yeah, what's the n here? 20. The x? 9. And the p? Which is roughly?
0.15.
1.5. Okay, so 1 minus. Why what? 1 minus.
It's 1, the answer.
Oh, okay. So they rounded it up to 1. So this here is
Oh,
0. Now it's not quite 0, but
it's
it's
like,
close to
okay,
0.
it's
Yeah.
like 0 point.
That's it.
Wait, my brain. N is 20, X is 9.
Guys, can someone give me the value here, please? 29.
0.9998.
And this is 20.
0.9998.
0.9998. So that's equal 0.0002. So what do you think? Reject or not?
Yes.
Yeah, oh, very much so.
Yeah, very much so.
Yeah,
I have a question.
go on.
How many marks does it for the exam?
6.
Is it like
1,
should be 10 or
2,
9?
3, about 5 or 6.
Okay.
Try number 7 now. Yes, try number 7 now. In 15 minutes. You have an appointment?
Yeah, I have a meeting with Sharon.
At what time?
30 or 40.
You can leave a couple of minutes early if you need to.
Okay, thank you.
Try number 7. Haza, come on, try number 7.
Drug number, but drug. So when it's test this claim, you should do all the steps after. Like in
Yeah, null alternative.
So like, if it says 20%, that means the H null is 20, but the alternative is more than 20.
Could be more than 20 if that's what they're saying.
Yeah.
Yeah, improves recovery rate, yeah.
So it's more than 20.
Yeah. Or you could just give it as a sentence that the drug improves recovery rates. All right, let's have a look at it. Now, what is the null hypothesis? It was basically that the drug has no effect, isn't it? Yeah. Yeah, and the alternative is that improves recovery. So is it 1 or 2 tail?
One.
One.
Yeah.
One.
No,
One.
it's one.
Yeah.
But
Yeah.
if it said that,
If it said alternatively affected recovery rates,
should be two.
it would be 2.
Okay.
Yeah. Yeah. Okay. Now, one tail. Okay. P-value.
20%.
0.2.
Yeah, well, hang on. How many people actually improved, got better? 5. And how many were we testing?
15.
So can we say 20%?
15.
Or 3 or more? 3 or more? Or
No, hang on. No. 5 people got better,
Yeah.
which is good. And what would be more extreme than 5 people getting better? 5 or more. Yeah. Guys, you need to listen. 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 Okay? So just think about this for a moment. I have a group of people, and I have some drug which treats them, helps them get better. So maybe in the group of 20, whatever it was, 20%, what's that, 4 people? Yeah, no, but normally 4 people would get better, naturally enough, okay? Now this is looking kind of bad for our drug, because how many people did get better? I think I said, what was it?
5.
Oh no, it's not great, is it? I mean, we were expecting 4 people to get better quickly, and how many people did get better quickly using this drug? 5, and we were expecting 4. So, is this a good sign to begin with for the drug?
Yeah. But what did you expect?
No, hang on. Listen. Is this a good sign, yes or no, for the drug?
No.
No, not really. I mean, if I have 20 people and I was expecting 4 of them to get better quickly, and it turned out 5 of them got better quickly, do I think the drug had an effect, or maybe just by luck one person got better quicker than normal? Well, probably by luck, right? Yeah?
But why did you expect 4?
Oh, because it said in the question that 20% of people normally get better quickly. Yeah. Is that okay? Yeah. So look, 5 people got better quickly, which is good because that is more than what we thought would be the case, 4 people. So what would be more extreme here than the 5 people getting better?
4, 3, 2, 1.
More than 5. That's more extreme. By the way, I'm using more extreme as a synonym for, more outrageous than what normally would happen. Okay? Like if all of them got better quickly, that would be quite extreme, wouldn't it? Yeah? Okay. Now, here's the thing. 5 or more, what's the problem here with using our tables? The or more is the problem. So we need to change this into, we have 2 choices here. We can change this into a statement about people getting sick, or we can do the -1, yeah. Now we just need to think about what would happen, because that's what I didn't do last time. So n equals 20.
15.
Is it 15? Thank you. Oh, is it 15? I thought it was 20.
No, 15.
Okay, well then in that case, if there was 15 people, we were expecting 3 to get better, and we got 5. Okay, that's actually a little better then. n equals 15, x equals 5, and p equals 0.2. How likely is it somebody will get better normally, not special? 20%, I said in the question. Yeah? Now, look, we need to think about what we want to do to fix the or more. So in our mind, let's think about the 2 possibilities, okay? If I was to change this into 1 minus not, let's see what that would. So this would be 1 minus not 5 or more getting better. What's not 5 or more people getting better? 4 or fewer people. Now, will that work? Yes, because 4 or fewer, the p is okay. Yeah? So it's fine to do 4 or fewer. So this would be 1 minus the probability of 4 or fewer. So we take out our tables and we look up n is 15, x is 5, and p is 0.2. And what do we get here? 1 minus what?
1 minus 0.938.
9, 3, 8, 9. Okay? That's roughly 4.1% or something like this. No, sorry. That's roughly 6.1%. Reject or do not reject? So is this evidence in favour of the claim that the drug is having an improvement on recovery rate, or not evidence? Yeah, yeah. Now, of course, it's possible that the drug actually is making people better. It's just we don't have enough data to conclude that from this experiment. Yep. Oh, sorry. Thank you. Thank you. If I put in 4, does that change things for the company? We'll change it a little bit, but will it change it enough? Speak up. What? 0.8. Oh, it's much worse now. 8, 3. Oh dear, that's even worse. What is it? About 16% roughly? Whatever. It's something like 16%. Okay. Yeah. It's worse for them. Yeah. So we do not reject the null hypothesis. Okay. Yep.
You said it's worse.
I mean, it's worse for them because we're even further away from 5%. Yeah. At what point would we reject the null hypothesis? At 5%.
Yeah.
This is 16, right?
And this is 16, roughly. I don't know what it is exactly, but it's clearly more than 5%. Are we getting our heads around these? I hope so, because it's nearly killing me. Right. I want you, as the last example, you can go to your meeting now, Alex. I want you, as the last example, to do question 9. Now. Stop moaning and do number 9. Timmy I have, don't I? Yeah. Haza, Alex, Kabul, Aziz, David, Sabrina. Yeah, there you are. Is it a full house? Amy I have. Peter, Raymond, Barack, Priscilla. Yeah. Patrick.
Yeah.
Joshua. Where?
Yes, there.
Joshua, Vanessa, Emma, Dana, Ishpreet, yeah. Mo. Yeah, I do have everyone. Come on, guys, calculate.
Number 8?
No, number 9.
This is 2 tails, right?
Let's see. No, it's 1 tail, because she's claiming that she can correctly predict what you're thinking.
70% or less?
No, it's going to say 80%.
But never mind.
Maybe 0.5.
Hmm? one more minute. Okay. So, in this one here, you got an answer?
No.
Okay, but it doesn't matter because whatever answer you get, you'll be wrong.
Oh.
Yeah.
You can't get an answer from the information given.
Yep.
Exactly.
So the problem here is that I'll give you, it's not enough information, and I'll give you an example, okay? No, I'll give you an example. No, David, please stop being weird, okay? I know it's difficult, but please. Okay, so you have here house, square, David. Oh, sorry. I thought that was you acting in Egypt. Sorry. Circle. Okay. So I want you to look at these four symbols. Now, I'm not sure if these were the four symbols, but it gives you the idea anyways. I want you to look at these four symbols, and I want you to pick one of them and keep them in your mind, and don't change your mind. Have you got one of them?
Yeah.
Now, it's important that you be honest. So whatever one you pick, keep it in your mind. Okay? So this, now I've seen this before on TV, so the idea was, oh, I can transmit and read your mind even over the television and so on. So, for example, did you pick the star?
Yeah.
Star? Star? Yes? Yes? Star? No? Yes? Yes? No? Star? No? No? Yes? Yes? No? No? Yes? No? Star? No? Star? Star? Yes? 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 Do you think I got star more than 25% of the time right? Yeah. Am I psychic? No. No. What was the mistake here to assume? The mistake was to assume the null hypothesis that people would pick each one equally. That was the mistake. That's the same mistake in the question you just did. Okay? It was wrong to assume that people would pick cats and dogs equally likely. It's, the example I gave in the answer was, it's possible that the person is in the Muslim tradition, and so people perhaps naturally would pick cats over dogs, right? Yeah. Because dogs are, yeah. So maybe this fortune teller, okay. It's an unclean animal. Yeah. So look, listen, it's possible that all this fortune teller is doing is just saying cat.
Yeah.
And if people pick cat 70% of the time, then how often will the fortune teller be right? 70% of the time. Just like with this example, it's possible that most people are picking star, and so me just asking did you pick star makes it look like I'm right a lot, but I'm not. Because the mistake was to assume that each one is equally likely, just like it was in that question about the cat and dog. It's not the same as flipping a coin, is it? It's wrong to think of this as flipping a coin, so to speak, just like it was wrong to think about that. Now, you should remember that one, because that's a common way people get tricked.
Yeah.
Okay? Alright. Anyways, please finish that at home, and we can do more in the tutorial. Am I right in thinking cats are unclean? No, dogs are unclean. And dogs are... Oh, I didn't say... I never hate. They're unclean animal. Cats. And dogs?
No, dogs are unclean.
Oh, they both are.
No, cats are clean.
Oh, cats are clean and dogs are unclean. Yeah, yeah.
Cats are gross and disgusting.